right? So what we are given is, we are given a function of this custom array using which we can find what is the element at any index in this entire array. Even if we are going about higher indices, what is the maximum element, what is the element stored at that index, we can get that. And it says basically if you go out of bounds of the array, it will return 9999. It's kind of 6 nines it will return. Two more things keep in mind is, numbers in this array you can assume they are of this range. The numbers will be from 0 to this, and they can be repeated also. So this is a new thing I'm adding. This should be the clarifying questions that we ask. So we don't know how many elements are in this array, but this is a range of the elements, and elements can be repeated duplicates also. So it doesn't mean these many elements are there. Elements can be double, triple of this, because if they are repeated, array can have more size. Now what we have to do is, we cannot know the size of the array. We have to provide an efficient way to search a given target. So example wise, if we take, imagine if I say 200 is the number I'm searching, 200 is my target I'm searching, so my answer that I'm expecting is 4, because 4 is the index at which 200 is residing, and we can return -1 if the value does not exist. Example for that would be, we take 6 as a target. If 6 is the target, our answer should be -1, and if 20 is our target, our answer should be 2. That's the index at which it is stored. So array is sorted. We have to think of a way which is better than O of n, because certainly O of n approach we can work out. We can start going from left to right. We can keep matching every element with the target that we are searching for. If it matches, we can return that index. But that linear search is not the choice here, not the option here. Now what can we do? So most of people get stuck here thinking like, since this is sorted array, I could have applied binary search. But for binary search, I need a left and a right, because the approach of binary search says, first you target entire array. So this is our search space between left and right. And then what we do, we find a middle. And by finding a middle, we compare our target to the middle. Since the array is sorted, at this comparison, we make a decision. Either the element is found here, that is first possibility. Second possibility is element lies on the left side, because if element is lesser than this, it will be on the left side, and if element is greater than this, it will be on the right side. So based on this comparison, we make a decision and we cut the array into half. So imagine we found the element to be in the first half. Then we repeat the same process. We find the mid again, then we compare the element, and this time imagine the element is in the right side. So we keep doing that. Initially we go with n size search, then we reduce it to n by 2, then we reduce it to n by 4. Like that we keep doing until unless we are left with one element where we can make a decision the element is found or not, right? So this is the binary search, but in order to do this we need left and right, and here right is not known because size of array is not known. Now what can we do about it? So this approach gives us some clue that here we are doing half every time, right? So can we take similar approach and come from bottom up? We can keep doubling every time. So this is the thought process we are taking. What if we take the doubling approach and we keep on increasing from small range, we keep on increasing to bigger? Now you would agree for sure, if that is the case, eventually the way we are looking at is, I'll just write it here. So if we write a for loop, imagine if for I is equal to 1, I is equal to n, I greater than equal to 1, I is equal to I divided by 2. That means if we write a loop which runs like this, starts from n, gets divided by 2 every time and comes till 1. This is one way of writing this loop, but we can write this loop from the other side also. We start with 1, we go till n, and we say I becomes I into 2, right? So then both the things would be same. In one case we are coming from higher value to lower value by dividing. Here we are going from lower value to higher value by multiplying. So binary search, this time we will apply from the other side, starting from smaller size and going higher. Now let's see what that thought process is, or what that approach is. So since the left and right are not known to us. So what I'm doing is, let's just take the thought process. Let's say I'm starting with left as 0. So this is the thing I'm doing. And right, I'm starting from any random number, but I want to choose a small number. So here in this example, let me take R as 3. Now, it's not essential that we have to take 3. We could have taken 4. We could have taken 1 also. But I'm taking a random guess so that approach is clear to us. So we took L as 0, R as 3, and that is where we start our approach. So what we do, imagine the target we are searching for is 200. That's the number we are going to search for, the first tracing that we do. Now what we do, we can compare our number 200 with this R and see 80 and 200 we compare and see whether our value resides on the right side or on the left side, right? So the range I'm considering, keep in mind I'm considering L to R range, and what I'll do is going forward I will double up this range, and then if I don't find in that range I'll double up again. So I'll keep the doubling approach. That's the idea, that's the gist we are going to, right? So if 200 is not equal to this R, what does it mean? Can we say it means that 200 is on the right side of this point? So the first thing that we said is, if the target value we are comparing, let's compare it with, if T is greater than A of right, then what we do, we have to go to the right side. That means we are discarding this entire left side. Now the way to discard that would be, this can become our new left. So I'll say my left is equal to whatever is the next index after right. So my left point starts from this, and right point I just double it, 2 into R. 2 into R. So what we do is, our range now, if you see overall, it has become, we are able to consider 2R elements in the next iteration, right? So that is how we would go about it. So it becomes 2R, and we have talked only about one case where our value is greater than this. So now since it is 2, it is 3, ideally R would become, let me put few more values, 900 and 1000. And post that, imagine there are no other elements, 5, 6, and imagine this is the boundary, and post that we will get 99999 as an answer. So we are here, our value was greater than this, so we go on to the right side, so left becomes this, right becomes this. Now what we do, based on this left and R, again we compare our value we are searching for 200 with the right. So I compare it with 1000, and what it tells me is, this is my second case, this was my first case, case 1. My second case I'm working out is, what if my target is less than A of R? If that happens, my target is less than A of R, what should I do? That means the range that I am looking for in now, this is the range that is my aim, because my left became 4 and my right became 6. So in this range I want to go and search again. So now if you see, eventually this has become a binary search problem, because here we know left and right both. So what we can do is, we can apply the approach. If our value is less than R, for sure we know our answer is in between. So what we can do is, we can take advantage of middle, and middle in such a way that we know we are reducing the size to kind of left remains left and R becomes left plus right by 2. So we are squeezing the search into this range. This is what we are coming to now, right? So that is how we go in case 2. Now case 3 would have been, the value we are searching for would have matched. Let's see going forward whether we come to that point. So for now what I have done is 4 plus 6 by 2, it has become 5. So we are saying this 5, which is the middle, I put my right as this. So my left has become 4 and right has become 5. This is the state we are in right now. Again, let's compare our value 200 with this right, which is 900. Our value is still less than this. So what we do, we say, now my right will again become L plus R by 2. So it's 5 plus 4 by 2, which becomes 4. So eventually we come to the same point. And now we have to look for terminating condition. The moment my left and right become equal, I know there is only one element in the array. That's my decision making point. If they have become equal, can I compare the value I'm searching for? Is it matching? It does. So we immediately say we found the answer. Right. So this is one tracing of this code, And approach wise, we have seen what we are doing is we are comparing with the right side, because right gives us the boundary, and then we are finding the element. And in this way, if you see, we are able to apply the binary search. Now you may ask, like, how is this log n time complexity, how it is better than n? So if you see, eventually earlier we were searching in a range L to R. If we are searching in L to R, possibility is if our element is found in between these two, then anyways we are doing binary search, because we are finding the middle, we are reducing it to half. That's how we are going. So in this case, there is no doubt that this is log n. The doubt is only in the other case. What if the element is on the right of R? So even if element is on the right of R, first think of it, first we were searching in size in this range of, imagine 2, let's say left and right were 2 distance apart. So if it is on the right, what we are doing is we are expanding our search space to 4. Because we are saying R becomes 2R. And if again it lies on the right of it, we make 4 as 4 into 2, 8. We make 8 as 16. So every time we are expanding, if at any point we hit a bottleneck, like beyond 16 there is no answer, so next search will happen between these two, because these anyways we discarded. So next search will happen between these two, and that search that we are doing will be again a binary search in a small range, but the way we are expanding, if you see, this becomes a log n solution. So this is approach and way to think about solution to this problem.